In this video, I'm going to present to you the whole chapter of ammonia in 3 parts. The first part, I'm going to talk about reversible reaction. The second part, I'm going to talk to you about the Haber process. And very importantly, you have to remember the conditions and explain to me why these conditions are used in the Haber process. In part 3, I'll teach you, and for that matter, refresh with you the displacement of ammonia from ammonium salts. Part 1. This whole chapter is centered upon this equation. In this equation here, nitrogen reacts with hydrogen to produce ammonia. And you will recall, in this case, that this is not a balanced equation. You will actually need to take, one hydrogen molecule to react with 3 hydrogen in order for me to give me 2 ammonia. This means that in reaction, you need to have a ratio of nitrogen to hydrogen in a ratio of 1:3 by volume. Okay? Now, in this case here, you will see that this arrow here, is a double-headed arrow, not something that you commonly see in the past. This arrow represents a reversible reaction. Now, a reversible reaction, you have to remember, goes forward and backward at the same time. A reversible reaction goes forward and backward at the same time. Now, what does this mean? So this means, this equation here, is actually comprising of 2 equations. One, the forward reaction. Conventionally, when we will look in this way, when this arrow points to here, from left to right, that would be your forward reaction. If this is in here to here, this is what we call the backward reaction. Now, which means that if I were to ask you to just write the forward reaction, it will be like this. The forward reaction basically is the reaction of your nitrogen gas with your hydrogen gas to produce, for me, my ammonia. Because now I'm writing the forward only, I'll use a single-headed arrow like what you guys usually do. But when it comes to asking, if the question asks you to write the backward, now students, here's the thing. When it comes to writing the backward, you must write it in such a way that whatever appears on the beginning of the arrow comes first. So this means it becomes 2NH3, becoming, for that matter, in this case here, decomposing to produce 1 nitrogen and 3 hydrogen. Now, in this case here, as long as I write this way, whatever that appears on the left-hand side, of your arrows, they will be known as your reactants. Whereas whatever happens on the right-hand side of the arrows, they will be called your products. So in this case, reactants becoming products. And this, students, is all you need to know about reversible reaction for now. Part 1 is over. Now, the second part. Now, in this second part here, I'd like to introduce you this industrial process, otherwise known as your Haber process. Now, this Haber process, is actually an industrial process that produces ammonia from your nitrogen gas and your hydrogen gas. Now, before I go on to show you how this entire process works, there is one very important part which you must remember, and it is the condition by which this reaction can take place. Now, this reaction, right, must take place at a temperature of 450 degrees Celsius, a pressure of 250 atm, and using finely divided, okay, and I highlight finely divided iron catalyst. Now, these are the three conditions, 1, 2, 3, which you must remember when you are describing the Haber process. Now, why are these conditions are chosen? Well, what happened is that over the years, right, the scientists, okay, have done many experiments. What they found out is that in order to give me the highest yield of ammonia, they actually try out the different pressure and different pressure. So what happens is that if they try out at 600 degrees Celsius, as they increase the pressure, right, they discovered that the yield gradually increase, okay, until a certain pressure where it doesn't increase that much, but generally you want a high pressure. So as a result of this, the pressure, you want it to be as high as possible in a way because it favors the yield. They also realized that if they were to conduct the same experiment at a lower temperature, the yield also increases for the same amount of pressure. So as a result of this, if we really want the temperature to be low, because based on this research, it shows that the lower the temperature, okay, the higher the yield. Which technically means, right, that as long as I have a very low temperature and a very high pressure, I should increase the percentage of my yield. But however, student, you will realize that in this case here, yes, it's true, we want the temperature to be low, but we cannot be too low. Now, why so? Well, if the temperature is too low, right, you'll find that based on what you understand in kinetic particle theory, when the temperature is low, the molecules move really slowly. So as a result of this, right, the reaction, okay, will become too slow. Okay? This you must remember, you don't choose a temperature that's too low, because if you do that, reaction will become too slow. So as a result of this, after some experiment, trying out the various temperature, scientists discovered that 450 degrees is the optimum temperature, where you get a decent amount of yield without causing the reaction to become too slow. Now, when it comes to pressure, right? Now, when it comes to pressure, things, okay, become interesting, because yes, it's true. If I can increase the pressure as much as I can, right, I would actually get a, high yield. However, you must realize that high pressure also means, number one, you're going to use very costly machinery, because you need to make really expensive, strong machinery that can withstand the pressure that is going to hold without causing an explosion. Number two, okay, to generate high pressure, okay, is expensive too, costly, costly to produce high pressure. Because what happens is you need a very high pressure, you need a compressor to compress the air at very strong force in order to actually produce a high pressure, and that itself is costly. So after doing some experiment, they realized that, hey, after 300, since it's not going to increase so much, I'm going to use, a pressure that is somewhere in this range, and comfortably it becomes 250 atm. Now, you also need the use of a catalyst. A catalyst is basically something that speeds up a reaction without itself being changed. You use finely divided iron catalyst, and with these three conditions, you should be able to produce ammonia at a situation where you get just the right yield. Now, next, let me explain to you how to describe the Haber process. Now, in order for you to easily remember and describe the Haber process, I want you first to remember for me this funny looking shape here. I have a box here, they have two arrows pointing this way, okay? And then on the other side, okay, I will have reaction point this way. Okay, so what happens is on this side here, I will have my reactants, and on this side here, I will have my products. So now what happened here in this case here, we all know that in order to produce ammonia, you would need your nitrogen gas. You will also need your hydrogen gas. Okay, your hydrogen gas. Now, what you need to remember is how we obtain this gas. Well, please remember that your nitrogen is obtained by the fractional distillation. Fractional distillation of liquid air. Okay, do remember this. Okay, fractional distillation of liquid air will give you nitrogen. Please remember that. Now, to obtain your hydrogen is by this process called cracking, which you will learn in later chapters. Now, it is by this process by letting petroleum, okay, undergo this process called cracking. So it is the cracking of petroleum, okay, that will produce for me, okay, your hydrogen gas. Now, always remember that because you are describing how you're going to make this, you will have to mix, okay, nitrogen gas and hydrogen gas in a ratio, okay, in a ratio of 1:3, okay, by volume, okay, you mix them, okay, and what happens is you pass them through a chamber with, okay, remember what the condition, which is at a pressure, okay, pressure of, we call number 1, pressure of 250 atm, temperature 450 degrees Celsius, and last but not least, you will also need your finely divided iron catalyst. Okay, so once that happens, right, what you will produce in there, in the chamber, is number 1, you have your ammonia gas. But however, you will also have your remaining unreacted, okay, nitrogen as well as your hydrogen gas. Okay, these are the unreacted. Okay, these are your unreacted, okay, hydrogen and nitrogen gas. So what happens is when they pass through this part here, they will all be a mixture of gases. Now, because it's a mixture of gases, when they pass through here, what they do is they cool it. Now, because your ammonia have a higher boiling point than your nitrogen and hydrogen, okay, just for your information, okay, your boiling point, okay, of your ammonia is actually negative 33 degrees Celsius, okay, your hydrogen, okay, the boiling point, okay, let me just check this out quickly, okay, your hydrogen boiling point is negative 259 degrees Celsius, and your nitrogen boiling point, right, is around negative 193 degrees Celsius. So what happens is when the temperature is lowered, right, see the big difference over here, what happens is if you maintain the cooling, okay, temperature at just somewhere in the like negative 40 or negative 50, you will of course cool down your liquid, your ammonia, while having your nitrogen and hydrogen remaining as gas. So what happens in this case here, you will get condensation, okay, and what you do is in this case here, you will produce your ammonia, but now this ammonia, okay, is in liquid state, okay, take note, liquid state. So, and then this will be removed, and this is what you want. So of course, for your hydrogen as well as your nitrogen, they will still remain as gas. So what happens is they are then passed through, okay, channel back here, where they can be actually reused so that they are not wasted. And this, students, is how you can describe your your Haber process. Some additional information you may want to know. Okay, this Haber process is actually an exothermic reaction. Okay, which means in this case here it gives off heat. Okay, gives off heat. And also for that matter, right, even though we get all these really great, awesome conditions, right, the yield is actually still pretty low. It's only just a 10%, okay, to 15% yield. So you can imagine if they didn't make this better, the yield can actually be even lower. So this is the Bond-Haber process. End of part 2. Take a break if you want, okay, at this point of time. Now I'm going on to part 3 of this chapter. Welcome back. The last part of this chapter, right, is we are just only talking about one very simple reaction, and that reaction is simply this: an ammonium salt what happens is when you react this together with an alkali. Okay, you react this with an alkali, and from what you guys know, right, when you actually put them together, and if you have a reaction, okay, generally you could also, sometimes it will happen by itself, or sometimes you need to do a little bit of warming. Okay, you will actually produce your ammonia gas. As well as another salt, in this case here being the anion of your ammonium salt and the cation of your alkali and water. In this case here, this is what we call a displacement of ammonia from its salt. Ammonia is actually first found inside this ammonium salt upon reacting with my calcium hydroxide. Okay, what happens in this case here, in the process of either heating warming or heating, you actually, in a way, remove your ammonia gas. Okay, and as a result of this, right, it gets displaced by the alkali. You see, this metal part here sort of kick off your ammonia and produces another salt and water. Now, for all those of you who are in my class, right, this should not be too unfamiliar. This is actually the first locus point where there is the cleaner holding the bag with the ammonium salt. When you put in sodium hydroxide, which is also an alkali, and you warm it, the cat came out, and the cat represents your ammonia. So for those of you who are in my class, this should not be something that should cause you to be stressed about or be frightened about. Just recall the first locus point in the memory palace. Now, so what does this imply? This implies, right, that when it comes to a practical use, this is this. Well, I have my ammonium salt. And ammonium salt, right, students, is actually a very commonly used fertilizer. Now, what happens is in this case here, right, a very commonly used fertilizer in agriculture. Let me just check my spelling. Okay, yes, it's a S. Okay, for those of you who may be looking up, it's a S, fertilizer. Okay, fertilizer. Okay, what happens is when a farmer add this fertilizer into the soil, okay, the whole idea is that you want to introduce nitrogen inside the soil. Okay, soil wants this. Okay, but however, okay, an alkali, in this case, especially the case of calcium hydroxide, right, this is actually a very good agent, okay, to increase your pH. Okay, so what happens is if you're gonna if you're gonna add fertilizer and then you add another alkali just to increase your pH to grow particular crops, because recall, some crops need particular very specific pH to grow. What happens is you're gonna cause ammonia to be formed, and ammonia, if you recall, the boiling point, okay, is negative 33 degrees Celsius. Okay? When it's formed, it will just become a gas and then it will just escape. And the process of escaping, right, your nitrogen, which is what the soil wants, is removed. So what happens as a result of this, you should never add an ammonium salt and then immediately add in another base. Okay? So with this marks the end of chapter 17.